ferroelectric, supercapacitor, EMI shielding, and so on. And it's very interesting to see that he has started his career from industry, that TFCBL Chandigarh. Then he moved to IIT Kharagpur as an assistant professor. So then he moved to IIT Patna, and present he is associate professor from 2011. So regarding this PhD guided, that he has guided 8 PhD students and 8 PhD students, 11 MTech students, and 11 MSc students. And ongoing PhD students is 4, ongoing MTech student is 1, and publication, that is really interesting one. He is having 75 journal publication, that very cited publication are there, and books and proceedings, that 25, invited lectures at 28, citation that one can see that it is approaching to 1000, and so, and he has completed a number of the very interesting their projects. So projects, it is going to be of 89 or 90 lakhs. So apart from that one, he is also active in institutional activities, as he is professor in charge, coordinator of faculty affairs, and so many other things are there. And academic awards and honors, if you see, then he is nominated as member of National Committee to review roadmap for RCI technology, etc. Then member of the National Committee of Advanced Energy Research Center, gold medal for securing first position in first class in the merit MSc examination, editorial board member of an international journal, the Open Energy and Fuels, associate editor of an international journal, Journal of Applied Sciences, Engineering and Technology, editorial board member of an international journal, Journal of Plastics and Polymer Technology, editorial board member of an international journal, Journal of Research Updates in Polymer Science, and he is recipient of the Best Paper Award in 11th Asian Conference on Solid State Ionics held in Coimbatore, Best Poster Award for the poster presentation at 6th Asian Conference Solid State Ionics, and Best Paper Award at Recent Trends in Materials and Devices in 2010. So doctoral research work, his doctoral research work that was reviewed by Professor Koba asked me that Niigata University, Japan. So he is having a very big list, and one can see is he is recipient of the prestigious Nehru Fellowship sponsored by Jawaharlal Nehru Memorial Fund to visit this University of Singapore. And future plans, that he is well focused. So he has given his future plan, that materials and device development and optimization, scaling up the device performance parameters for exploring commercial feasibility, strengthening collaboration in India and abroad in common area of interest. So with this brief introduction, that I would like to invite Professor A.K. Thakur, and the topic of his talk is the need for clean and green energy alternatives, pros and cons. So over to Professor Thakur, sir. Professor A.K. Thakur, now you can continue, please.
Yeah, very good morning to all the participants, as well as Professor Pandey for giving me this opportunity to interact with all the participants as well as the MNIT community. And without wasting time, since time is limited, perhaps I would get 2 hours.
Yes, sir. Yes, sir.
Okay. So normally I have a habit of talking too much. So whenever time is over, please let me know.
You are most welcome, sir. You are most welcome. Please continue.
Yeah. So now I'm switching off my video because it will hamper the speed, and I would come again in video mode at the end of the talk. In the meantime, let me share my slides. Is the screen visible now? Slide is visible?
Yes, sir, it is visible. It is visible. You can make this full screen,
Yeah.
please. Yeah, that's good.
So we the topic of today's discussion, I had focused on the current requirement what worldwide people are hankering after. So we know since beginning of the civilization, energy is an essential tool for sustainability and would remain so. However, when one set of energy becomes threat creating sustainability itself, then an alternative is need for an alternative is felt essentially. And this is what we are facing currently, the entire world is facing currently because of this growing pollution, increasing temperature, threat for sea level rise, creating serious threat for the coastal major cities in the coastal area around the world. So these are few very important challenges. There are many challenges, but these are very important challenges that is likely to threaten survival and sustainability of civilizations across the globe. So now when the need for an alternative comes, then there are four important energy alternatives that we all know. I would quickly list them. First and foremost is solar energy. But unfortunately, solar energy, though its cost has gone down drastically, it is still costly enough when we compare to the conventional fossil fuel alternative. And the second major difficulty with solar energy alternative is that it's not a stand-alone device. Mostly we can convert solar energy through entrapment during day, but more, we need it more in the night when sunlight is not available. As a consequence, we have to have a storage cells for storing the energy during day over and above that is left out, and then ensuring the supply through inverter mode from the stored battery packs or cells. However, when it comes to cells and battery packs, they are standalone energy alternatives. So there are two varieties of alternative energy sources that we have. One is photovoltaic and fuel cell. Both of them come under the conversion class of energy alternative. The solar cell converts the solar energy into DC power, whereas fuel cells, they convert the chemical energy stored, chemical energy of a reactant into DC power through conversion mechanism, as long as supply of fuel and oxidant is maintained. However, in storage devices, which works on little different principle than the conversion devices, chemical energy is stored in the device itself, and it can be delivered when a load is put across it. So batteries, rechargeable batteries, and even the non-rechargeable primary cells as well as supercapacitors come under the class of storage. Since Professor Pandey had briefed that this is a storage device based workshop or symposia, so I am restricting now onwards on storage device general principles. So in general, a storage device, whether it's battery or capacitor, comprises of several compartments consisting of at least 5 components. Two components on the extreme are current collector. One is there may be two electrode in battery. We call it anode and cathode that facilitate redox action. And the anode and cathode are separated by an intermediate compartment that can be a separator filled with electrolyte, or in solid state cells, a same electrolyte can also function as separator. So in solid electrolyte based cells, the separator also serves the purpose of electrolyte as well. In general, there it has therefore 5 components which are essential to assemble a storage cell, whether it's a battery cell or capacitor cell. In capacitor, we don't have normally anode and cathode. We call it electrode 1 and electrode 2 if the supercapacitor is symmetric. But if the supercapacitor is asymmetric, then again we have there 2 electrodes that are different, and in both the cases they work on different storage mechanism. One is based on non-Faradic and another is based on Faradic mechanism. So in today's discussion on storage cell fundamentals, our prime objective is why is it so important? Then brief history of storage cells with focus on batteries in general, and its basic principle and origin of energy in such cells, tools and importance considering the design aspects and mechanism of operation, and then different classes of battery that has been developed since now, followed by few case studies where prime focus would be on the work that we are currently doing at IIT Patna. As Professor Pandey mentioned, I started my basic PhD work itself in the area of storage cells, and I have continued it till date, from where I can claim today that from concept level understanding in the very beginning to today, our group has reached to the product level status, which we will discuss today, citing few examples, not many, because time is limited. So why is it so important? If you look at let us impose a question on ourselves, whether battery research is not new. It has a history of almost over 200 years old. Now, whether still this area has reached saturation or not, the answer is not. Why? Because with question of achieving clean energy alternatives, there is enough scope to go up and up on this ladder, starting from first rechargeable cell lead acid, followed by nickel cadmium, nickel metal hydride, lithium ion, lithium metal potential, and lithium polymer, and all solid state lithium battery, which is the ideal requirement for electric vehicles that is being talked about worldwide for phasing out the fossil fuel based energy alternatives. And the acid, no matter whatever be the technology, the acid test of performance for any cell is measured in terms of a plot of power versus energy. And this plot is known as Ragon plot. Let us take the simple example of vehicle requirement, which is very important. The green energy concept is now to be put essentially under use to protect our environment in order to protect life on the earth and have sustainable life cycle as on a continuous basis. If we compare, then there are serious challenges. The gasoline and on which the conventional vehicles are running, and its replacement with electric vehicle, where batteries or a combination of battery and supercapacitor or fuel cell will ultimately drive the vehicle, depends on primarily that there is a huge power delivery gap. And if this gap can be filled up, then and then only the saturation in the battery technology may be said to have been achieved. Therefore, though its history of this storage cell research is pretty old now, but there are lots to be done still, and the biggest challenge is operational safety when we talk about use of storage cells in electric vehicle applications for drive on road and safe drive. So, in this continuation of safe drive, the current challenges are cell component processing and proper design and its fabrication, ideally required by electric vehicle, and then its packaging and configurations so that both electrical as well as thermal safety features are achieved, and what are the safety features that must be implemented, and what are its protocol for developing safety elements for a battery pack for EV applications, that we will be talking at some length in today's discussion. Going back to the history of battery development, ancient to present, it started some 1800 year old, in the year 1800, with voltaic pile, where silver zinc was first considered to create voltage and deliver current. And then later it was taken to the next stage by Daniel. Then in 1859 by Plante, the rechargeable lead acid cell, first rechargeable cell, came into effect. The first two voltaic pile and the Daniel cells based on silver zinc or copper zinc combination were non-rechargeable cells. And then came another primary cell, that is Leclanche or carbon battery. Am I audible? Because there is a background noise.
Sir, you are audible, and some audience that he has opened his that let us mute him. Yeah.
Okay. And then
Sasi Bala, please mute your mic. Sasi Bala, please mute your mic.
battery development has moved forward. Battery development has moved forward, reaching the stage of lithium ion in 1991, when the first commercialized lithium ion cell was demonstrated by Sony Corporation Japan. And in between the first rechargeable lead acid cell and lithium, there were several developments addressing the safety issue of lead acid cells, then maintenance issue of the lead acid cells, and it was Gassner and commercial flash Junger who first addressed the safety issue in nickel cadmium as well as the plantain based lead acid cell. Finally, sealed lead acid cell came into existence in 1970, which we call today maintenance free valve regulated lead acid battery. However, it is not maintenance free. Still, we need to replace water and acid from time to time periodically in order to maintain its power delivery status at the desired level of specification. And then finally, it developed further from lithium ion, and in 1999, concept of lithium ion polymer started into effect with prime focus on developing low temperature battery for without freezing of electrolyte, liquid electrolyte of lithium ion. And then lithium ion polymer has now also become a reality, and now people are talking about all solid polymer battery at elevated temperature, because in vehicle on drive temperature would go rising. So either we have to create a design for heat dissipation or create a design with appropriate material that can function well with adequate thermal stability which is desired during operation of a vehicle. Because in lithium ion, where still electrolyte is liquid in nature partially, will get leaked, and in lithium ion polymer, the polymer component that works as the electrolyte may melt at relatively higher temperature, because the thermal stability of polymers is always a question mark. So this is how from voltaic pile the cells have grown as of now. These are the conventional lead acid cells which we use in our lab to power online UPS or inverters. And then nickel cadmium, this is valve regulated lead acid battery. And then we have lithium ion secondary cells, which is embedded within the equipment itself. So the battery technology, as it has grown, the demand on its performance in terms of voltage, power, temperature of operating temperature has gone up across. So here is the performance parameters of all the primary battery systems that has been commercialized, and then among the secondary batteries, the lithium ion system, which lies at the bottom, was first commercialized in 1991, and its desired performance is not at the level required in the temperature limit from -20 or even beyond this in the subambient region, and here it fails. But as far as room temperature application is concerned, it has served us nicely, and it would keep us serving nicely. And secondly, when it comes to electric vehicle applications, so until or unless alternatives are searched, it can still serve the purpose there, provided the thermal design of the batteries pack is made in such a way that temperature doesn't go beyond 50 degrees. So performance, when we are talking about so critical applications for battery, then its performance comparison, as I told, is measured in terms of Ragon plot, which is nothing but power density and energy density plot. So if we look at, for vehicle requirement, we have two types of power requirement. One is when we drive uphill or at the starting point, that we require little larger power. And when we go on constant drive at a constant acceleration, then the vehicle requires a constant power, not very large power, constant power to maintain the speed. So when constant power is required, then we require large energy density to last it long. But when we go uphill, or when we have to change the gear, or when we have to start the vehicle, then we require large power density. It means it is at this stage that sometimes batteries are said to have, if we look at here, batteries are said to have, rechargeable lithium battery, large energy density, but sometimes it lacks large power. And at this stage, when we require large power to be coupled with large energy density for long driving range, along with fast charging attributes, then a hybrid combination of supercapacitor and battery is needed. And this is what we require, and therefore new developments are still needed for sustaining the electric vehicle plans around the world, and the battery technology has not yet reached the saturation stage. Say, for example, for photovoltaics, a small energy density would work. However, the for battery applications, we require both large energy density as well as large power density. And if we compare lead acid with lithium ion, then the performance is more than double performance parameters. So one of the biggest advantages is that lead acid has very short lifetime, whereas lithium ion or lithium polymer would have more than double the lifetime for the conventional lead acid or nickel metal hydride cells. Now, when cells are becoming, or storage cells are becoming so important, when storage cells are becoming so important for in terms of energy delivery, then we must know what is the origin of electricity generation from such storage cells. Definitely it is based on the basic principles of thermodynamics. The phase, the change in Gibbs free energy of the reactants in the course of redox reaction at the anode and cathode. That change in free energy that occurs is responsible for converting chemical energy into electrical energy, and as a result of this conversion, the EMF E is created due to activity of the electrodes, anode and cathode, that arises primarily due to the difference in the standard electrode potential of the anode and cathode, and F, the Faraday constant, basically gives us how many charge has passed through the combination comprising anode and cathode with separator and electrolyte embedded in between when such a redox reaction basically occurs. And here in general one term N is put, and this value N refers to how many charges have taken part in the redox action. For monovalent cations like lithium, there would be the value of N would be 1, hence the relation for lithium ion battery would be del G is equal to minus EF, where del G is the change in free energy as a consequence of redox action, E is the EMF generated, and F refers to Faraday's constant, which has for 1 molar mass of reaction, its value is constant, that is 96,500 coulomb. The electrodes, for such operation and such reactions to occur, the electrodes must allow ions to flow through them. Means at anode, oxidation would occur such that the ions that are generated would travel through internal compartment from anode towards cathode, and the electron that is released as a result of oxidation travels through external circuit. And if the rate of mobility of both ions and electrons are identical, which is expected for low molecular mass ions, then reduction occurs, generating again the lithium metal here and resulting in the mobility of equal number of electrons, creating current. So mobility of ions occurring through the intermediate compartment from anode to cathode is essential for redox activity to be redox activity requirement to be fulfilled, and the electronic charge that moves through external circuit gives rise to current. So the current arises, origin of current in a storage cell lies in the mobility of ions and electrons, whereas the origin of voltage lies in the difference in a standard oxidation and reduction potential. That is, difference redox activity basically determines the voltage. So what happens to the lithium ion that moves towards cathode? For this to occur, the cathode and anode structure both must have layered structures with sites and layer spacing at least equal to or little larger than the cationic radii. Otherwise, the lithium metal ion will not be able to undergo successive charge-discharge cycle, and it would cause volume expansion, undesirable volume expansion in the electrode, creating rupture and large rise in resistance at the electrolyte cathode as well as electrolyte anode interface. Now the question is, how many such charge we can store on cathode and anode? So definitely this redox action resulting in creation of voltage and current is a surface phenomena, and because of the surface properties, if the surface area is larger, then large number of such charge can flow, and therefore the cell capacity would be larger, and therefore nanoscale materials are considered ideally suitable for cathode and anode design. Next question, any end user is primarily concerned with cell capacity. So what are the factors on which capacity of a cell would depend? Energy, how much energy can be delivered, and what are the factors on which it depends? Power and its combination of energy and power, that is expressed in terms of Ragon law. So at this stage, I must say that capacity of any storage cell primarily depends upon how much mass is able to flow from one side to, so because here, as we have seen, in the operation of a storage cell, both charge transport and mass transport is involved. So charge and mass transport ultimately determines the cell capacity, and the rate at which the charge is being collected determines energy and power. Normally, a cell can have a cylindrical design or prismatic design for industrial applications. However, in a research laboratory, for judging the suitability of a material, coin cells are fabricated in general. We will discuss all those things. So genesis of energy, as I mentioned, basically lies in any electrochemical cell, this is how it has started. So in the previous, if we consider only anode and electrolyte with a reference electrode, it is called as half cell. And when we estimate cathode behavior, then a cathode and electrolyte combination with a reference electrode is known as half cell. And when two half cells are connected together, then it becomes a full electrochemical cell. And this is what it is shown here in the conventional zinc copper cell, which was the first voltaic cell, silver zinc and zinc copper cell that was developed. In this design, the redox action, oxidation occurring at this end and reduction occurring at this end, cathode end, ultimately determines how many charge and how much mass has undergone transported from one end of the electrode to the other end of the electrode in the cell design, and that ultimately determines the cell capacity, energy, and power. In equilibrium, the rate of charge and mass transport becomes constant. So most Popular electrodes are for the anode side gold, mercury, silver, copper, lead, nickel and cadmium. Whereas cheaper electrodes, metals like iron, zinc, aluminium, manganese, sodium, potassium and lithium were proposed much later. Almost it took 200 years. The idea was to develop a cell that can create more number of charge transfer at a lower mass. And till now, large number of charge transfer for a given mass, a smaller mass, type design has not yet been achieved. If we look at in iron, there is a possibility of 2 or 3 charge transport, but its mass is much larger. So except lithium, and now people are working towards sodium, which has not yet reached the stage of success. Potassium, magnesium, aluminium, zinc batteries are not yet possible in a for with long cycle life and high energy density. Now, a storage cell. We will have a quick look on the classification principles and technology which is available. So, electrochemical cells are broadly classified into primary and secondary. Primary cells we can use one time and then rechargeability is not there. This feature is not there. And a secondary cell can be charge discharge for a large number of cycles depending upon the design and material properties of a specific combination of secondary cell. There are a large number of secondary cells which has been already commercialized. The most popular and first secondary cell was lead acid, and therefore from there this concept of rechargeability started, and lead acid cell is still ruling the market, and it is all around us, and hopefully it will remain for another 30, 50 to 50 years down the line, because to phase out this would be possible only when its cost and performance ratio of the upcoming technology of lithium based designs or sodium based designs would be matching. For lithium, it becomes very difficult to match. Performance is definitely very high, but cost is not low or comparable to lead acid. Whereas in the case of sodium, it can be achieved. So until or unless sodium cells based rechargeable cells are commercialized, the chances of fully phasing out lead acid seems little difficult. So initial energy storage technologies were flywheel based, batteries based and ultra capacitor based. And the prime rechargeable technologies are lead acid, nickel cadmium, nickel metal hydride, lithium ion, lithium polymer and sodium ion, magnesium ion. People are working on this around the globe just aimed at bringing down the cost and fully phasing out the lead acid. Let us have a quick look on their performance. If we look in terms of performance parameters, lead acid optimal OCV is 2 volt, nickel cadmium 1.2 volt, nickel metal hydride 1.2 volt, lithium ion has 3.6 volt. So it has much larger edge. A specific energy density, lead acid hardly 1 to 60 watt hour per kg, whereas lithium ion is between 3 to 100 watt hour per kg. A specific power less than 300 watt per kg, it can go up to from 100 to 1000 watt per kg. So if we look at discharge time range greater than 1 minute, it can start discharging from 10 seconds to 1 hour. So there are large number of parameters on which lead acid has no edge in comparison to lithium ion, But in the cost factor, it still has edge, and people around the globe are working on two different aspects: bring the cost of lithium ion battery down and also develop alternative technologies like sodium and magnesium ion batteries that can match or be close in performance to lithium ion, and naturally the cost would be much lower than that of the lithium ion. And this is what the storage cell research has not yet reached the level of saturation. And in fact, I must say at this stage that a storage cell technology has a very bright future ahead for coming century, in the coming century, 21st century. Here is the comparison of in performance of rechargeable with non-rechargeable cells. Non-rechargeable cell still have a very sharp edge over lithium ion itself because of its longevity. It can last longer, as long as 10 to 20 years without being any degeneration in its storage capacity. So once it is designed and developed and produced, until or unless we use, there would be no leakage of current, there would be no self-discharge, and therefore it can last after up to 10 to 20 years. Whereas lithium ion battery has a discharge rate of around 1% per month, whereas lead acid cells has a discharge rate of around 8 to 9% per month. And this is why when we don't use our vehicles, that is using lead acid for starting ignition, then after 2-3 months its energy goes down and ignition creates a problem. It creates another problem in the winter when there is chilly weather, that at that time also it creates problem in ignition. The characteristic features of a cell may be size, longevity, discharge characteristics, the potential drop and flatness of the discharge curve, cost, and behavioral factors such as temperature, like storage and operation conditions, self-discharge properties, and memory effect. In fact, nickel cadmium and nickel metal hydride have memory effect. So at whatever discharge rate we have stopped it at any point of time, when we switch it on, again it would pick up at the same rate. So in case if we require little higher rate of discharge at the next use, then it creates a problem. And environmental factors such as leakage, gassing, toxicity, and shock resistance. So definitely we have to look forward for the next generation cells, and therefore different varieties of primary cells that are in the market currently, we have to look beyond them. The standard zinc carbon batteries, where chemistry is zinc and manganese oxide. Features are they are inexpensive, widely available, inefficient at high current drain, however, and poor discharge curve, poor performance at low temperatures. Then we have a standard alkaline battery that we quite often use in our remotes of television or air conditioners, etc. That is based on, that has different varieties like AA, triple A, etc. And it is based on zinc manganese oxide with potassium hydroxide aqueous electrolyte. Its features are 50 to 100% more energy than the previous one, zinc carbon. However, low self-discharge. It has this is another advantage, and it can last 10 years, up to 10 years, if not used. Good for low current, up to 400 milliampere of current drain. However, its discharge curve is poor. flatness is no longer there at the desired level. Sloping discharge it has. Heavy duty zinc chloride battery, its chemistry is zinc manganese dioxide. Features, it has better resistance to leakage, it performs better at high current drain, and better performance at low temperature. When any cell performs better at high current drain, that property is known as rate capability of the cell. Say for example, if our power requirement for 5 or 10 or 20 second is 2 ampere and the cell can deliver at the most 1.5 ampere, then such cells will not be useful for that specific application. And there is another lithium primary cell, that is lithium manganese oxide, manganese LiMnO2, and in fact lithium manganese dioxide reactivity, when extended further, it gave rise to lithium ion rechargeable battery. And it promises high energy density, long shelf life up to 20 years at elevated temperature of up to 70 degree. It is capable of high rate discharge. However, it is expensive. Whenever lithium comes into picture, cost naturally goes up. So a typical alkaline manganese dioxide cell design, primary cell design, is in the cylindrical shape, has a large number of components inside it. So it has a metal casing with polymer plastic coverage from the top and bottom for safety of sorting, battery sorting, cell sorting. And it has a positive cover electrode at the top, and the bottom is with metal spur that acts as the negative electrode, and metallized body comprises inside the zinc rod or MnO2 rod, and then we have alkaline electrolyte like KOH, and there is a plastic film level separating the anode and cathode, and its discharge curve, if we look at, is slopy as I mentioned. So its big issue of all these primary cells are sloping discharge. So as we start consuming power, it will go drain, and ultimately after some hours of continuous use, it will fall, and it becomes unusable because it cannot be charged back to its original energy level. So here is primary battery applications. No doubt there are segments where primary battery applications are still ruling, and that is zinc carbon is widely preferred in flashlights, toys. Heavy duty zinc chloride is used in radios, recorders. Alkaline, all of the above use. Lithium manganese dioxide with large power density, normally in cameras and photo flash, and so on. However, as we keep on draining power, its voltage would fall down, and at critical voltage limits, the performance would cease. Secondly, the voltage window also is very limited, from 1.6 or 7 to 1 volt. So potential window of operation is also very small. But its biggest advantage is, once designed and produced, until put to use, there would be no self-discharge behavior until up to 10 to 20 years. So that way it is highly useful when its application in a specific segment is concerned. Coming back to secondary or rechargeable battery, which is going to be utilized in our variety of applications where we need to use the batteries on continuous basis over longer period of time. And the candidates are lead acid, the historical first lead acid cell, later nickel cadmium cell, nickel metal hydride cell, alkaline cells were also developed for rechargeable, but its parameters and applicabilities is in a very small segment. Then came lithium ion cells or lithium ion batteries, lithium ion polymer batteries, and now futuristic cells are, I must note it down here, futuristics are sodium ion batteries, zinc, then lithium air battery, lithium sulfur and sodium sulfur. They are the futuristic candidates that would rule the electric vehicle market in maybe 10 years down the line. Round the globe, people are working on these in these area, and IIT Patna is also working on that direction. When it comes to lead acid, any query in the primary cell segment? Please, if anyone has any query on the portion covered till now, please feel free to interact. If there are no queries, then we are moving to the secondary cells. The first, here is a one thing that I must tell. First lead acid cell was developed by Plante, however, he could not patent it. And later on, Jugner developed it and also modified it little bit and patented it. And Plante lost his rights since he had not secured his IPR. And then Plante's name remains only in the textbook and classroom discussions, whereas the entire technological intellectual property right was secured by Jugner. So a lead acid battery components are positive electrode or cathode is lead oxide and the negative electrode anode is lead metal. And in the electrolyte that works here is sulfuric acid in distilled water. And the separator are nickel mesh kept in between of the box to separate these two electrodes, and electrolyte and ions keep on moving from anode to cathode in the course of reaction through the mesh. So how does it operate? The negative electrode is lead and the positive electrode cathode is lead oxide. So when this combination is created by keeping all the components inside a box, then at anode lead first oxidizes into Pb2 plus, creating 2 electrons, and these 2 electrons resulted as a result of oxidation at the anode end travels across external circuit, and the lead ion in between, which is released into the electrolyte, combines with sulfate ion of the H2SO4 and creates lead sulfate. Here, since there is aqueous electrolyte H2SO4, so it ionizes into 4H plus ion plus 2 sulfate ions. So 2 lead will combine to create 2 lead sulfate, and this is how the ions created and released into the electrolyte facilitates movement of lead ion from anode end towards the cathode end. What happens at the cathode end? At the cathode end, the sulfate ion and the lead again reacts to produce lead sulfate, and overall reaction is Pb plus PbO2 plus H2SO4 releasing PbSO4 plus 2H2O. As a consequence of this, 2 electrons have moved through external circuit from anode to cathode, and 2 lead ions have moved from anode end to cathode end, and the byproduct of the overall reaction is PbSO4, which again ionizes into lead and sulfate ion and gets deposited at the cathode. So this reaction produces an overall nominal voltage of 2 volt per cell, and when such cells are connected in series, then we can get 6 volt lead acid pack or 12 volt lead acid pack or 24 volt lead acid pack or 48 volt lead acid pack. Right now, there are large number of e-rickshaw that are being fed with this 48 volt lead acid cell. However, its speed and its range of travel is very limited, and that is why, though the concept of battery run vehicles, it has helped a lot in demonstration in reality and field trial. However, to achieve larger range, larger life cycle and large power delivery, lead acid based auto rickshaw or e-rickshaw are being replaced with lithium ion battery based battery packs, lithium ion cell based battery packs, and this is how the demand of battery pack manufacturing has gone up manifold, and this is the hot topic of research as well as commerce today. The reaction that is occurring in lead acid battery is demonstrated over here, as I explained already. So the reaction mechanism in lead acid, as I said, as the battery discharges, sulfuric acid concentration decreases, and at the same time lead sulfate is deposited on the electrode plates. So when charging follows the inverse process, but a small portion of the lead sulfate always remains on the electrode plates, and this causes sulfur poisoning of lead acid cell electrodes, which we will discuss in detail later. Typical internal design of a lead acid cell is here. Each cell comprises of a grid plate, meshed grid, separating anode and cathode, positive electrode plate, a negative electrode plate, and microporous separator, grid type separator in between, and this constitutes a single cell. And if large number of such cells are connected in series and packed inside a box, then it gives a 6 volt or 12 volt or 48 volt combination, depending upon how many cells are connected in series. This is one part. And here is a pack comprising 12 volts, and if we will find corresponding to each cell, we have valves here, so that whenever water evaporates, water shortage, distilled water shortage inside the pack occurs, leading, yes, please. Yeah, I'm listening. Is there any query? Okay. And the typical lead acid discharge curve is here. If we look at the lead acid discharge curve and its cell voltage as a function of time, then a typical discharge begins at 2 volt, the open circuit voltage of the cell, and it follows a more or less sloping behavior with a small plateau in between. And so here is the one discharge and then charge. So discharge charge behavior of a lead acid cell that depends on occurs in the very small window of the voltage limit, and therefore a single cell lead acid would not be considered ideally suitable for applications to replace primary cells or nickel cadmium cell. But when we have a large number of such cells in a battery pack, then we can think of using it. So this is the typical lead acid battery discharge where plateau region is very small for a very small amount of time, maybe 30 minutes to 30 minutes per cell at the most. And this was first patented by Unbuki and Pascoe, the students of Jugner. And here are valve regulated lead acid battery performance characteristics at different current load developed by Tyco Electronics. And this Tyco Electronics has developed a battery pack of 12 volt, and here is the discharge curve, 12 volt, 100 ampere. So if we draw energy at the rate of 25 ampere, it will discharge for as long as 2 to 3 hours, and if the current rate is increased, then the discharge time gets shortened drastically. So the battery charging method for lithium, for lead acid, can be done in a variety of ways. Constant voltage discharge or constant current discharge or taper current or pulse charge discharge, we can do it. However, one of the biggest disadvantage of lead acid cell is that always it requires float charge to continue, otherwise its current or voltage would fall drastically as a function of time. And therefore, in the float charging, controlled voltage and controlled current has to be maintained throughout, and this is what happens in inverters that we are using in our household or UPS that we use in our offices. So the moment we use the power goes, the desktop computer UPS is normally depending upon the battery pack supporting it. If there is a single 6 volt or 12 volt battery supporting it, it doesn't last more than 30 minutes for both CPU as well as monitor. So the ideally recommended lead acid battery charging methods are constant voltage or constant current, or sometimes constant current followed by constant voltage. The third option, constant current followed by constant voltage, is considered ideal method of charging, because when we charge through constant current method, then as a function of time, it allows optimal voltage to be achieved. But the net designed energy may not be achieved, and for that constant voltage charging is a mandatory requirement, and the same is done in the case of, for same charging method is adopted for lithium ion cell as well. However, constant charging and constant current and constant voltage charge is also used for lead acid, but these two options may not be suitable for energy storage and charging of a lithium ion battery. The reason is very simple. With constant current charging, voltage is achieved very fast, but net energy at the desired designed level may not be achieved, because large number of ions need to be pushed back from cathode towards anode end. The right way to charge a lead acid is, if it is designed for 2 volt, which it is, then it has to be charged to 2.4 volt per cell and slowly allow its voltage to fall down up to 2.2 volt per cell under float charge condition, so that when the charger is removed, the voltage would stabilize at the rate of 2 volt per cell. The lead acid battery performance evaluation, or in general any other battery performance evaluation, is also can be done through a empirical law governing rate of discharge developed by Thakur in 1897. It depends upon how long a cell or a battery pack would last. It depends upon how much current we are drawing, how much is the ultimate design capacity of the cell or battery pack, and how much is the designed capacity of the battery pack. Means how much is the rating. When we buy cells, lithium ion cells for our mobile phones, we say 5 ampere or 5000 Ah, 10,000 Ah. So this is what the rated capacity of the cell it tells us. And this rated capacity of the cell tells us, it basically depends upon how much molecular mass has been stored in the cell configuration that is really taking part in redox action on putting a load across the cell. And the constant in this relationship exponent is Thakur's constant that has a specific value for different cell chemistry, and it also depends upon the rate of discharge. The specific value may vary from 0 to 1. For 1 ampere discharge rate, Thakur's law is often stated as Cp is equal to I raised to the power k into T, where Cp is the capacity at 1 ampere discharge rate. It must be expressed in terms of hour, means if the cell is 1 Ah cell. I is the actual discharge current, T is the actual discharge time in hours, and K is the Thakur's constant, which is dimensionless. So for lead acid cell, we can express this Thakur's law, which is the commonly accepted equation for capacity calculation. N and K are constants obtained by data of maximum discharge and minimum current. We can, for two different rates of discharge and the time taken in the two rate of discharge, the value of N we can calculate. And once we know and this N is the experimental data, and once we know the value of N, we can very easily calculate the value of K in that specific case. This is how the discharge behavior can be used to calculate the cell capacity with different rate of discharge and the ultimate discharge time taken, and the value of N estimated in each of the cases are shown on the slide. The limitations of Thakur's law is the effect of temperature on battery capacity is not included, which is very crucial in the case of lead acid cell, because if we increase temperature, first water of the electrolyte evaporates, and second, electrolyte density becomes thin, that affects capacity drastically. Battery age is not considered in this case because Thakur's exponent increases with battery age, and this is another limitation. And for a very low discharge rate, this equation never accounts the fact that each cell has a self-discharge rate. In general, the performance of any storage cell is evaluated in terms of a number of performance parameters. So the very important among them are the state of charge of a cell. It refers to how much charge is stored in the cell at any specific point at the time of design, and when it is put to use, then how much charge is left after a certain instant of time when it is put to use at a given load. This state of charge estimation is a very important for electric vehicles, because if 200 Ah cell is designed with a capacity of 10 kilowatt hour, then on drive the driver and the user must know after 1 hour of drive how much charge is left, after 1.5 hours of drive, how much charge is left, and it must be demonstrated also so that appropriate action on replacing the battery or charging the vehicle battery may be taken up. So it basically refers to the current integration to determine the charge in battery capacity over time. So basically it refers to the quantum of coulomb stored in the battery pack or cell, and therefore we can calculate it simply from the Coulomb's equation. Q is equal to IT. Depth of discharge, how low, up to how low voltage we can discharge the cell, and the cell after being discharged to such a level it can recharge again, because this is known as depth of discharge. If we cross the depth of discharge limit, then charging the cell would normally not be possible. So therefore, for all battery packs or cells, an upper and lower limit of voltage is fixed, and this limit is known as voltage range for operating the battery pack or cell. And this lower limit is also known as terminal voltage. Open circuit voltage is the voltage of a cell or pack when there is no load across it. And internal resistance basically depends upon the interface resistance built after each and every charge discharge cycle. Now we must know when a cell is being charged or a cell is being discharged. Then what is the effect of temperature? What is the effect of load? And what are the phenomena or mechanism of action? How does it proceed? So most circuit parameters depends upon a state of charge discharge rate, and temperature. Here is a clear effect of temperature in a commercial cell. At 40 degree, at 20 degree, it performs very well. If we increase temperature, as I mentioned, electrolyte thinning and electrolyte water evaporation occurs. As a consequence, performance dies down. And when we reduce temperature, then also its performance dies down, because water freezing is the natural consequence at zero itself for aqueous electrolyte. And if some anti-freezing agent is given in the design, then it may not freeze sharp at 0 degree, but there would be drastic drop in performance and current delivery rate. So it becomes very important to understand what are the mechanisms that occurs. So whatever we have discussed till now, it was basically the cell design and cell performance aspects. Now we enter into the mechanism that delivers voltage and current. So in a cell comprising 5 components with two current collectors on either end, sandwiching anode and cathode, in between which electrolyte and separator stage, stopping the direct contact of anode and cathode. So if we look at the two ends, then at the two ends of the cathode and current collector and anode of end and the current collector, we have resistive barrier, and this is known as lumped resistance, Rm plus at the cathode end, Rm minus at the anode end. And this lumped resistance arises because of metallic current collector in bulk resistance, and all the lead wires and plates that are metallic, they join at their resistance has to be added together both at the cathode and the anode. So this is known as electrode resistance at the interface of electrode combination with the metallic current collectors. Then comes the intermediate compartment. Now anode is also connected with electrolyte at one end and cathode is connected with electrolyte on the other end. Here there is a voltage. The cathode redox potential in this case of PbO2 is 1.69 and anode redox potential is minus 0.36. It is known as cathodic potential, which is positive, anodic potential that bears negative sign, and when we add them together, the net EMF difference across the two combination adds up, giving a voltage close to 2.1 volt to the lead acid cell. Now in between, at the cathode electrolyte interface and the anode electrolyte interface, charges migrating in the course of electrochemical reaction get deposited, and as a consequence a charge accumulation occurs at this interface and this interface that gives us double layer capacitive effect. So double layer capacitive effect at the interface between the positive plate surface and the electrolyte CdL plus and the negative plate surface and the electrolyte CdL minus occurs, and this CdL basically double layer capacitance depends upon effective surface area of each plate and the battery state of charge, and it's a combination of series connection basically behaves as if a double layer capacitor is embedded, permitting charge storage. Then another component is charge transfer resistance. When anodic and cathodic reaction occurs at this interface, then charge cations and anions migrate internally and electrons migrate externally, creating current, and this gives rise to charge transfer resistance at the interface of the electrode and electrolyte, and the rate at which such a charge transfer reaction occurs ultimately determines the current delivery rate or time lag or resistance that will be creating joules heating in the design. Then we have bulk capacitance and bulk resistance. This bulk capacitance arises because of the electrolyte material and resistance of the electrolyte, and equivalent resistance of the electrolyte material is referred to as R bulk. So when a cell operates, as we have stated, that there is an internal migration of ions and external migration of electrons in general, creating voltage and current and facilitating oxidation and reduction at the two electrode ends. But in between, at each of the interface, we have capacitive and resistive effect that definitely affects the power rating of the device. So in modeling the circuit, battery modeling, we must use, depending upon the redox action that is occurring in the course of cell performance, we must take into account the resistive and capacitive effects throughout the design, and if power is to be improved, then these effects are to be controlled at the level of design and material selection itself. So Randall's developed his own equivalent resistance circuit model for simplifying the battery action. Here we present the Randall circuit model in a simplified way. However, for it, yes,
Slide.
Slide is
Yes,
not
sir. Please
visible.
continue. Please continue, sir. Please continue.
No. Let me see the slide if it is not visible.
No,
Is it not?
no, it was visible, sir. It was visible. Yeah, visible, sir.
Visible? Okay, fine.
Yeah, visible. Yeah.
So this is the simplest approach to present the Randall circuit model. However, those who are interested in its rigorous analysis of circuit modeling of battery, they can consult the book on impedance spectroscopy by MacDonald, which is a very popular book. in research for this aspect of analysis. So for modeling, we have to proceed in a modular way. In the first step, we have to ignore bulk capacitance since its magnitude is much larger than that of the double layer capacitance at the anode and cathode end. In step 2, we have to add the resistances at the interfaces and the bulk. The electrode interfaces Rm plus and Rm minus and the bulk resistance of the electrolyte so that material resistances which is bound to occur can be taken into account. And in the step 3rd, we have to add the two potential difference, two voltages at the standard electrode potential of the cathode and standard electrode potential of the anode so that its a final model can be arrived. So all the resistances can be expressed as the sum of series resistance at one end and then charge transfer resistance, diffusional resistance due to mobility of ions and the double layer capacitance forms one RC circuit on the anode side and another RC circuit on the cathode side with a voltage, net voltage across the cell. It means the overall performance of any battery, not only lead acid, can be simply modeled electrically as the series combination of two RC circuits in series with net resistance arising due to the materials used in the design of the cell and the RC circuits, two RC circuits are just cascaded RC circuit that arise due to double layer capacitive effect and the resistive effect of the materials at anode and cathode end are cascaded in series across the device. So two series combination of two RC in series with resistance of all the components can be the simplest possible model for determining the battery model. And there are several such models have been presented. However, with this simplest model, the net resistance, which is nothing but the net internal resistance of the cell, and the net capacitive effect we can very easily calculate, and from there this circuit the charge transfer resistance at the anode and the cathode can be evaluated because it is very important parameter because we know how is the kinetics of the charge transfer because that ultimately determines the current rating and power rating of the device and the power losses that will be occurring when a load is connected. So this is how the simplest model, and this simplest model can be further reduced as a single RC considering the equivalent capacitance and equivalent resistance, and we can calculate the cell parameters through cell testing results, and hence at what level, at what rate charge is migrating inside we can calculate through charge discharge plots, and as a consequence we can visualize just like a photograph each parameter how the cell is migrating, how the ions are migrating, at what rate electrons are migrating through external circuit, whether there is any ion pairing occurring in the case of, in the course of travel of ions, cations from anode towards the cathode and vice versa, and all these effects can be calculated and quantified. And this is the importance of circuit modeling in the case of a battery. And the same Randall circuit model can also be used in the case of lithium-ion battery as such. Now, without going into, can I extend for half an hour, Professor Pandey?
Uh, Sir, yeah, time is there. Yeah, 1:30 up to 1:30 that you can continue,
Yeah, yeah.
sir.
So you give me 30 minutes, I will close. So merits
Okay.
of the and demerits of less. The biggest problem with lead acid is sulfation. Means sulfur deposit occurs and sulfate greenish layers we always find in our vehicles, and this is only because of the sulfation. When water deionized water inside the battery evaporates, and this and its gravity of the specific gravity of the electrolyte falls below 1.225 for a 12-volt cell, and in that case sulfation occurs, and hence the cell starts giving problem for with lower power, and now this signals degeneration of the cells. Secondly, sulfation hardens the battery plates, reducing and eventually destroying the ability of the battery to generate volt and current. It has very low specific density, limited cycle life, doesn't like full discharges. It gives, if it is designed for 100 ampere hour, it at the most we can draw 40% of the designed capacity. This is one of the biggest limitation, and the second biggest limitation is its bulky design and very heavy weight. Nickel cadmium and metal hydride battery chemistry are the next generation of rechargeable cell, where nickel and cadmium serves as the electrode and nickel oxyhydride works as the electrolyte, or KOH sometimes also. Whereas in the case of nickel metal hydride, on the one hand we can have lanthanum nickelate or titanium magnate with nickel hydroxide or potassium hydroxide as the aqueous electrolyte. Nickel cadmium is rugged, it has longer life, it is economical, it has good discharge rate, but memory effect is the biggest issue with this. On the other hand, nickel metal hydride has higher energy density, 40% more than that of the nickel cadmium. However, their voltages are very low. 1.2 voltage, open circuit voltage is 1.2 volt. And the memory effect and sloping discharge is there, whereas in the case of nickel metal hydride, a flat plateau can be observed. I can skip nickel memory effect as I have explained, no need to discuss it further. So now I would quickly come to, there are health concerns with cadmium, and probably in India also there was some times ago AMCO battery that dominated the nickel cadmium Indian supply. But unfortunately, because of the health concern of the people working on this development and the environmental issue, AMCO battery company in India has also been closed down. Now coming to lithium batteries. As I said, lithium batteries can be either in non-rechargeable mode, primary, as well as rechargeable. I think there is no need to emphasize the use of rechargeable lithium ion battery, because all of us are carrying it in our pocket. So we will go to its important features. It is lightweight, typically metallic, chemically resistant, and stable at cell voltage of 3.5 to 3.6 volt. It has flexible design is possible, and such a flexible design with polymer separators can be an added advantage over all the battery designs, in addition to its specific feature of large plateau, very low self-discharge rate, and compact design, and high energy and power density over the existing technology. Lithium polymer first started in 1970. It uses a solid electrolyte and requires 50 to 60 degrees centigrade operating temperature to attain conductivity. It can be used also using a gel electrolyte, and the typical configuration is identical. Anode is typically graphitic carbon. Whereas cathodes, there are several transition metal oxides, that may be lithium cobalt oxide, the first conventional one, for which Nobel Prize was awarded 2 years ago, 2019. Iron phosphate or lithium manganese dioxide, lithium nickel oxide. There are several lithium based oxides that can be used as cathode, and each of such oxides has different properties. But anode is in all the cases graphite. However, graphite has certain limitations, even though it has served us nicely, and therefore its replacement is being searched with some titanium based or some graphene or CNT based replacement. This is how the discharge occurs and charging would be occurring. It exists in several designs like cylindrical or prismatic and flexible designs. It of course comprises of anode, cathode, electrolyte and separator along with current collectors, and a flexible design comprises of copper and aluminum current collector on anode and cathode sides respectively, with plastic electrodes on the either side for sandwiching a plastic electrolyte fed with silica or plastic separator. Electrodes and electrolytes must have certain attributes, and the most important attributes are layered structure with adequate thermodynamic stability, should have high electronic conductivity, and should be capable of releasing electrons very fast, should have high surface area and pore volume, and should have adequate mechanical and strain bearing ability for better sustainability over longer life cycle. On the other hand, electrolyte must have ionic conductivity in the order of 10 to the power minus 3 to minus 4 Siemens per cm at room temperature, with ideally single ion conduction, only lithium ion migration, no anion migration. However, this is yet to be achieved. It is still a target to be achieved. Here are few electrodes, different chemistry where graphite remains the same, but cathode as the anode, but cathode changes. With change in cathodes varying from lithium cobalt, lithium manganese, lithium phosphate or doped lithium cobalt oxide, the performance parameters keep on changing with upper and lower voltage bracket and cycle life. The highest cycle life with a very large stable plateau is achieved in phosphate based and NMC based. However, plateau is much wider for phosphate than NMC, and therefore they are the two preferred candidates for electric vehicle applications. And they are thermally stable also up to 200 degrees centigrade, and therefore the lithium phosphate and NMC are going to be the potential candidates for upcoming EV as of now. Their charge discharge mechanism in both the cases are intercalation based with flexible volume expansion permission must be there. Diffusion of ions should be fast, and a specific capacity, however, is low. And the future requirement is that reaction may not be intercalation type. Even if displacement reaction occurs, it should be capable of sustaining large volume expansion, and high specific capacity is the need of hour. And this is how during discharge, lithium ions from the layered structure of the cathode travels across the separator and enters into the electrode, that is the cathode layers, undergoing intercalation, and during charge reverse action occurs. So in this case, if the volume expansion sustainability is not there, the electrolyte interface would rupture, creating serious issue, and therefore a layered structure with adequate layer gap is an essential criteria for a successful electrode in lithium ion battery application. There is no need to emphasize much on lithium-ion battery electrode material, which are the layered graphite structure. It permits lithium-ion intercalation. However, it doesn't work for sodium, and therefore, using graphitic anode, sodium-ion battery is not possible. Sodium-ion battery-based cathodes are available, but sodium-ion battery anode is still a challenge. The day this challenge is sorted out, sodium-ion battery would be a reality. Among the electrode layered structures, the potential candidates are lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate, lithium manganese silicate, and NMC, etc. Here are their attributes. Among these, as I said, lithium phosphate NMC is widely suitable for vehicle application, whereas lithium cobalt oxide and lithium manganese oxide may be suitable for all other applications. Our cell phones basically comprises of lithium cobalt oxide, cell phone batteries. The separators may be silica separator, and they must have porous and flexible structure. It should be electronic insulator. It should be ionic conductor, chemically resistant, and very stable in electrolyte so that secondary reactions are not allowed. Potential electrolytes may be lithium boron fluoride, lithium phosphate fluoride, lithium arsenic fluoride, and lithium perchlorate. However, LiBF4 and LiPF6 are widely preferred due to their lower molecular weight. And the solvents for such electrolytes are polar solvents like ECPC combination or ECDEC combination or ECDMC combination, or a quaternary combination of ECDMC EMC gives low temperature stability for up to -5 to -10 degrees centigrade. And this type of porosity must be there in a separator. The common redox mechanism is from the anode, lithium ion first. In the anode, lithium ion is to be inserted intercalated. So cathode 6 carbon atoms combines with X lithium to create LiXC6, and this Li comes from cathode, that is Li's cobalt oxide, releases partial lithium, creating a structure Li1 - X cobalt oxide with a X not more than 0.33, beyond which this structure would become unstable. So at the most, with lithium cobalt oxide or existing most of the lithium based battery technologies, full lithium ion intercalation is a serious challenge, and therefore it imposes limitations on voltage as well as design. Ultimate reaction is lithium cobalt oxide and 6 carbon creates one migration of X lithium ion, and this value of X is 0.33 at the most. And here is one component and here is another component sandwiched with sandwiching separator, creating a single cell. It may be a coin cell. The simplest laboratory-based architecture and design is coin cell type. However, when we go for industrial design, it has to be essentially cylindrical or prismatic, or it can be then and then only it would have meaning. Prismatic cell. These designs we have discussed in the beginning as well. And this pouch cell, in order to lower the weight factor, nowadays pouch cell is the ideal requirement for most of the applications, particularly at high altitudes, because it has lightweight and it is cost effective to manufacture. It has simple, flexible and lightweight design. It can protect the device or battery from exposure to humidity, hot temperature, etc. So these are the three best cell designs: cylindrical, prismatic, and pouch. Cylindrical has good cycling ability, long cycle life, economical to manufacture. Prismatic allows compact design, mostly used for single cell packs, and pouch cell is light and cost effective way to manufacture. Now, how to calculate a cell capacity in lithium battery? The cell capacity in a lithium battery, that is the total quantum of Coulomb pass. Theoretically, we can calculate how many ions are taking part in reaction multiplied by the Coulomb factor for 1 hour per, and what is the molecular weight? So this gives us milliampere hour per gram, where N is the number of charge carrier, F is the Faraday constant, Mw is the molecular weight of the active material used in the electrode. Since molecular weight of the electrode is in the denominator, always a lightweight electrode choice would create better cell capacity. For example, in the case of lithium iron phosphate, it undergoes a reaction theoretically, releasing one lithium ion, oxidation, and a stable FePO4 layered structure. So molecular weight of lithium ion is 157.7 gram per mole, with 1 N is equal to 1 lithium ion taking part in redox activity, Faraday constant taking to be 96,500. The net theoretical capacity Q, when we put these values into the upper equation, works out to be 170 milliampere per gram. It means if 1 gram of lithium iron phosphate is used in the design of a coin cell, it would be capable of delivering theoretically a cell capacity of 170 milliampere hour per gram versus graphitic carbon as the electrode or as the anode. And experimentally, the capacity has been obtained, reversible capacity, to the tune of 130 to 135 milliampere hour per gram, which is ideally very good. And in practice, we can calculate reversible capacity of any electrode, total quantity of charge passed by molecular weight of the material, and this is the simplest simplest way to calculate the capacity of a lithium ion cell. Manufacturing process of lithium ion cell is quite a lengthy process. It involves multiple stages. Basically, two processes are quite important. First one is electrode coating and the second one is cell assembly. The electrode coating requires coating of electrode to be done on the current collector, and then cell assembly requires, I think I can skip these details. And cell assembly requires anode component, cathode component coated on current collectors, and electrolyte components to be bought together as a final cell assembly, which can be expressed in terms of. And the cell assembly process involves a number of processes like stacking, connecting electrode, inserting electrode stack, and then sealing the pack, and finally charging it. Performance evaluation of a lithium ion battery gives us a very stable plateau over a large number of cycles. Now I would switch back to few work that has been done in our laboratory, skipping these slides which we have discussed at length. Lithium ion batteries, there are strengths, but weaknesses are there that needs to be improved, and particularly high power chargeability, fast charging needs to be addressed properly along with operational safety features. So today is a small window, but we have a wide window available for developing the things tomorrow with large power, large energy, and fast charging options. Here we have developed a nanocrystalline powder material in our laboratory to address high capacity. And if we look at, we have been able to obtain capacity as high as 1000 milliampere hour per gram with a specific electrode developed at our end. And when coin cell or prismatic cell was fabricated using this, these were the fabricated prismatic cell in our labs. The coin cell of dimension 1 centimeter square area and the prismatic cell of 60 mm into 30 mm dimension were developed in our laboratory and put to test. And larger size cells were also developed, and were used in running, preparing a battery pack, and field trial testing a e-rickshaw was done. Here is the battery pack developed at IIT Patna, and it was put to use in a conventional auto rickshaw, replacing the fuel engine with a BLDC motor and a battery pack. The battery pack dimensions are written: 600 mm length, 400 mm, 140 mm width, and 250 mm height. And it was inserted in our laboratory group. It was assembled and then put in a conventional auto rickshaw, and the moment battery connections were used, the speedometer started showing power, and it was put to use in the campus itself. Is the video visible?
Yes, yes, sir.
Yeah, it is visible. It is
Yes, sir.
visible,
Yes, sir.
sir.
So one of my students said, "Am I going to become auto rickshaw driver?" I said, "No, you will drive several people by creating such a innovation." And here is the online test report during drive. How much is the range of travel recorded through an app while driving? So one full charge allowed its drive of this conventional auto rickshaw to 71.33 kilometer in one charge that lasted for 4 hours 3 minutes with an average speed of 18 kilometer per hour. And auto rickshaw weight was 140 kg, battery pack weight was 38 kg, net weight including battery pack and auto rickshaw 178 kg. BLDC motor requirement was 900 watt of power, and this battery pack with a power of 3.3 kilowatt could deliver a test drive range of 75 kilometer per charge repeatedly for the last 3 months. Another development what we have done, lithium ion based compact online UPS, where the complete pack without any battery to be planted outside, as it happens in the case of the inverters that we use in our household. The net weight of, we have designed in 4 modules: 250 VA, 500 VA, 850 VA, and 1 kVA lithium ion battery inverter, whose lowest weight of 250 VA is 5 kg, and 1 kVA weight comprising all the components including battery pack is 16.5 kg. It is quite handy to carry, and it was dedicatedly designed and developed and tested for defense application at high altitudes under a DRDO funded project. And this 250 VA online UPS can feed the power to a CPU and desktop computer at our desk. It was capable of deliver power continuously for 4 hours 3 minutes repeatedly. And when we put printer also under use, then it can function, it can deliver power without any AC mains backup up to 2 hours. So this 250 VA lightweight compact lithium-ion battery-based inverter can be very useful for any desktop user in the anywhere with printing facility as well. Whereas the currently used 250 VA UPS with lead acid doesn't allow us the computer to last 20 or 25 minutes beyond if power doesn't come. Transporting lithium ion is also a big challenge, and therefore all the international guidelines have been framed by United Nations that no lithium-ion battery can be transported from one place to other for delivery at a charge rate of more than 20% SOC state of charge. There are safety issues related to overcharging, short circuit current, and damage due to electrolyte leakage. And this safety due to overheating can create burning, and this is what has happened in several cars using lithium-ion battery. However, this can be controlled, and this can be controlled using battery management system. The key functions of battery management system is protection and control over overcharge, over discharge, overcurrent, short circuit, and temperature range, so that no failure or burning of the battery pack occurs, particularly when it has a high power rating. And for this, IIT Patna, I am happy to declare our group at IIT Patna has designed and developed battery management system from concept to product level for both electrical performance control for safety and thermal management control, so that temperature doesn't go beyond the critical limit. And here are few products that has been developed in our lab specifically to feed the requirement of defense as per their requirement. However, they have not put any bar for civilian applications as well. We have patented all these aspects, and India is the first to develop this as an truly indigenous product from concept through design, fabrication, testing, and safety feature implementation and field trial as well. So whatever BMS for safety of battery pack you have seen in the auto rickshaw under test, that is the field trial success. And it has the feature of display also. If we have 4 cell pack here as it is under test, then battery and voltage and current on load, in each case this BMS can identify and display on the display panel, so that we know if any cell has gone bad, pack can be opened and it can be replaced with another cell, making the battery pack functional again, instead of rejecting the pack as a whole. This is the voltage limit and the current limit under display. Thank you. If there are any query, I am ready to address.
So let us thank the speaker. That's very nice presentation, sir. And we have seen so many applications there. Render circuit particularly, that is not covered anywhere, and you have covered here. That's a very good one, sir. So now session is open for the discussion.
Yeah. Can
if
I?
Anyone have
Yeah.
any query anywhere? Sachin Goyal, probably he has raised his hand. Sachin Goyal.
Yeah, please.
Any other candidate?
Yeah.
Sir, battery
Yeah,
capacity changes with temperature for lead acid battery. How it is possible? Battery capacity changes with temperature.
Yeah, because capacity basically depends upon how many ions are migrating, taking part in the redox activity.
Oh,
If in the case of lead acid, if temperature goes up, then electrolyte density changes, because there would be at a higher temperature, at increasing temperature, there would be evaporation of the water because it is aqueous electrolyte based. And
yes.
secondly, the as the water content goes down, sulfate deposition on the electrodes would also occur simultaneously. This is the reason why most of the time at regular interval distilled water is added into the lead
Four.
acid battery packs.
Okay, okay. Thank you.
Any other query?
Oh, please don't hesitate if you are having any query anywhere, because sir has done by his own research in his lab that you can see. There's
Yeah,
so
these
many
are
things
all
that he has developed.
our internal development, and perhaps BMS. Our
Yeah.
pilot facility was inaugurated by DST Secretary and DRDO Chairman. Both themselves
Oh, well.
declared, yeah, both themselves declared that this is the first in India, because these BMS are being imported mostly from China and Korea and Taiwan. And this is why in the EV, National Committee on EV, for this part, which is chaired by Niti Aayog member Dr. Saraswat, I have been made a member of that committee.
Oh, that's very good one, sir. Very good one. So I think that in different parts of the India, people are working very good research, but
Yeah.
industries are not coming forward. That's why we are unable to deliver it at faster rate.
Yeah, but
In
first, the people, Indian industry people, they are more interested in first looking at the viability and reliability of the people who are claiming from within the country, because maybe
yeah,
they have been earlier cheated, so they are very cautious and watchful on the reliability and viability of the developments, and that is why Niti Aayog has been roped in at a different level of at least EV battery pack and lithium ion battery development for electric vehicles applications. And as far as,
oh, this is happening.
yeah, this is happening.
Yeah, this is happening. See that one of my student, she got very good result, and
Yeah,
the potential window that was very high potential and specific capacity and energy density and other things, devices we have made. As and when
yeah,
we are sending her to a very good journal, they are saying that it is more suitable to editor is learning just by writing a line, that it is more suitable in other journal. So there is no, they are not forwarding that one for the review process. So this is happening sometimes. So any other question, please? So there is no further question. So it was self-explanatory, sir. That your presentation that was self-explanatory, and I have also enjoyed a lot. And
but I have
so
exceeded my
many things
time,
that
your time limit, and all of
what is
the,
sir?
I have exceeded the time limit given normally, because the topic was very vast to cover.
Yeah. But most of the things, sir, you have covered very
Yes,
well.
sir.
So, on my
Sir,
own
I want
behalf
to
and on
ask.
behalf of all the participants, I would like to thank you, sir. Thank you very much. Thank you, sir.
Thanks for
Thank you
this
very much.
opportunity. Maybe look forward to meet sometimes in person when this current phase is over.
Sir. Okay, sir. Thank you very
Thank
much,
you.
sir.
Thanks.
Thank you very
Yeah,
much.
thanks a
Now
lot.
you can leave, sir. Yeah. So, sir, you can leave now. No problem, sir. So, session is now open for the uh, attendance part that as I have shared. So, see that I'm going to share this only 5 minutes that within that. Oh, sorry. So it will take some 5 minutes to complete that one.